Okay, so last time we were talking about factors that affect solubility. We had talked about structure effects, like how polar dissolves polar, like dissolves like, that sort of thing. Second thing were our pressure effects. We talked about Henry's law, which was that our concentration in molarity was equal to Henry's law constant times pressure, and we also saw that as our pressure goes up, the solubility of a gas goes up. Okay? The third thing that I'd like to talk about is how temperature affects solubility. This should sort of be intuitive for most of you. Usually solids are going to be more soluble as our temperature increases. So if you think about it, right, say that you're making like sweet tea, right? What you can do is you can fit more sugar into that tea if you heat it up, right? So you always heat up your tea on the stove, then you add your sugar, then you cool it down. And that's because you can fit more sugar, more solids into that solution at higher temperatures. Now, usually gases are going to be less soluble as temperature goes up, okay? So let's think about this, right? We know that if we take a can of soda out of the fridge, right, it will keep its carbonation longer when it's cold, all right? And that's because, and as it heats up, it will get flat, right? It'll go and lose all of its carbonation more quickly as our temperature goes up. Okay, so gases are going to be less soluble, so they're going to be released as our temperature goes up. Now, also on slide 15, there's a couple figures at the bottom that show you, gas and solid solubility. Here's our solid solubility chart, okay? And what you can see is you have all these different saturation lines, okay, that go across, basically showing you that as your temperature goes up, in general, your solubility goes up as well, right? So as your temperature goes up, your solubility curve goes up. Now, this is our saturation line, which says that this is the maximum amount, okay, of sugar, in this case, that we can put into our solution, okay? Now notice that at a higher temperature, we can fit more sugar into our solution, okay? So if I was making sweet tea, I could heat it up, I could add more sugar, and then I could cool it down, and it would be over here in this region. This special region is called our supersaturated region. Supersaturated, okay? And that would mean that a sugar water solution that we had made over at this temperature and that solubility would be a supersaturated solution of that sugar, which means that it has more sugar in it than would be soluble at that temperature normally, okay? But we were able to do that by heating it up first and then cooling it down past our saturation line, okay? Now, those are going to be our three factors that affect our solubility in general that we're going to talk about. Now, another set of properties that I want to talk about regarding solutions are our colligative properties. So moving on to slide 17, colligative properties are those which depend only on the number of dissolved particles, not on the identity of the particles. So in other words, they matter on, or they depend on how much you can pack into that solution, okay? Some of these factors or properties are going to be vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. And I'll be going through each of those in our videos, all right? Now, before I dive into that first one, which is our vapor pressure lowering, I first wanted to talk a little bit about some of the properties that we discussed last semester, okay? So, let's say that we have a mixture of water and vinegar. All right, that's going to be like acetic acid. Okay, so let's say we have some mixture. Try to draw a little bit better beaker. All right, and we have H2O in there. We have our acetic acid, HAC. We have some H+. We have some acetate ion. All right, but we've got a mixture. Okay, now in the solution, we know that X H2O would be our mole fraction of water, all right? And we also know our XAC would be our mole fraction, or XHAC would be our mole fraction of our acetic acid, right, or our vinegar, all right? Because again, our X is going to denote the mole fraction in the solution, right, in our liquid, okay? Now, also, we know that pH2O standard, right, that's the little circle means, that circle means standard, that's going to be, right, this is our vapor pressure of pure water, okay? Again, that little circle is going to refer to it being pure, okay, and at standard conditions, all right? Now, if we heat this solution, then that means that both vinegar and H2O will go up into the vapor, right? You can kind of think about this, right? If I heat up this mixture, okay, I know that eventually I'm going to boil off this solution, right? And water's going to come off as steam, right? And we'll also have that vinegar smell that comes off, right? If you ever made pickles at home, or I guess that's probably something that most of you don't do, but if you were to make pickles at home or you heat up something, right? Even if you open up a jar of pickles, you smell that vinegar, right? And that's because vinegar is a volatile component. It's going to come off, right? So if I heat it up, I'm not only going to be pulling off the H2O, but I'm also going to be pulling off that acetic acid, right? So both of these components are volatile components, all right? So that means that since they both go up into the vapor, part of the vapor will be water and part will be our vinegar, right, our HAC, all right? Now, the part of the vapor, okay, so here we had our part of our solution, okay, that was our X sub H2O, so the part in the liquid was denoted with X, right, that was our mole fraction in the liquid. If we have the part of the vapor, right, the part of the vapor that is water is going to have the pressure, so it has the pressure or the partial pressure, I should say. It has the partial pressure given by P H2O, which is equal to X H2O, P H2O standard. Okay, so again, this was our pure H2O. We multiplied it by our fractions. This was our pure vapor pressure, right? And then we took the fraction that was water to get our partial pressure. So this is our partial pressure of H2O, okay, in the gas, right? And then this is our mole fraction in the liquid. And this is our pure component vapor pressure. So if we wanted to calculate our partial pressure of H2O in the gas, this would be how we calculate our partial pressure. We take the fraction in the liquid that's H2O, or the fraction of the liquid that is that species, and multiply it by what it would be if it were pure. All right? And you kind of think of it, right? Like, say that I had a pizza, right? And half of that pizza, or rather, let's say I had a pizza, and it's in thirds, right? And a third of it is pepperoni, and then 2/3 is onion, all right? Then that means that I took my fraction. If I wanted to know the part of the pizza that was pepperoni, right? I'm going to take 1/3 of whatever it would be if it were pure, right? One whole pizza. 1/3 was pure. So that means that my part of the pizza that was pepperoni is 1/3. Okay? If I had 2 pizzas that were this way, right? Then that would mean that the part that I have is the partial amount of the overall is going to be 2/3. Now, don't think about that too much, because I think it'll make more sense when we do a real example. All right? But continuing with this, right? The part, so that was the part from the water. The part that is vinegar is calculated the same way. We've got PHAC is equal to XHAC times PHAC standard. So if we took the pure, we multiplied it by the fraction that we had, that will give us our partial pressure. All right, so again, that's our partial pressure in the vapor. We have our mole fraction in the liquid and our pure vapor pressure for that component. Now, so now that we know that part of the gas pressure comes from each gas, if we add up all of the partial pressures, we'll get the total pressure. All right, so P total, our total pressure, is going to be the sum of our partial pressures. So that's our partial pressure of H2O in this case, plus the partial pressure of the HAC. All right, so that would be our total pressure in the gas, which is our sum of our partial pressures. Now, if we want the fraction of acetic acid in the gas, right? We know the fraction of acetic acid in the liquid, right? But if we want to know the fraction in the gas, and trust me, they're not always the same number. Okay, if we want to know the fraction of acetic acid in the gas, we're going to say that we have YHAC. Okay, that's our mole fraction in the vapor. Again, Y denotes the mole fraction in the vapor. Okay, and that's going to be the partial pressure in the gas over our total pressure in the gas. So P HAC over P total. Okay? Yes? So that means that if we put all of that together, right, we know then that PHAC is equal to the YHAC times our P total. In other words, if we take our total pressure and multiply it by the fraction in the gas, we will get the partial pressure in the gas. So that means that if we were to put those two equations together, we would see that we have the PHAC, right, the partial pressure of the acetic acid. We know that that is equal to our mole fraction in the liquid, HAC, times what it would be for pure acetic acid in the liquid, all right? And that's equal to also, we know that this is also equal to our mole fraction in the vapor, RYHAC, times our total pressure in the vapor, all right? So in other words, we have a liquid side and we have a vapor side, all right? Essentially, this is saying you can relate the concentrations in the liquid to the concentrations in your vapor, all right? Now, why is this important? Well, in our mixture of acetic acid and water, both of those components we said were volatile, right? They could come off, we could smell the acetic acid, we knew that we had water vapor, right? We know that both of them come off, right? But let's say that I have salt water. Let's say that you go to the ocean, you grab a bucket of salt water, and you pour it into a pan on your stove and you boil off that solution. The water's going to come off, but what you'll find is at the bottom of your pan, you'll have a bunch of salt, okay? Because the salt doesn't come off when you boil it. It gets left behind, right? Salt is a non-volatile component, okay? So if we were looking at our colligative properties, right, we were talking about properties that depend only on the number of particles in the solution. Well, salt is going to be a particle, right? Sodium and chloride, those are going to be particles, right? So the first one of our colligative properties that I want to look at is vapor pressure lowering. Okay? So, we have vapor pressure lowering. Now, if we have non-volatile components, right, that will result in a lowering of our vapor pressure. So having non-volatile components lowers your vapor pressure. Okay? So this equation up top, this is called Raoult's law. All right? And it says that X of a component, right? And I'm just going to call it A, right? We used acetic acid, but any component that we have, X of component A times P of component A pure is equal to the mole fraction of that component in the vapor times our total vapor pressure. All right? So again, that is our Raoult's law, okay? Now, if the solute is non-volatile, right? For example, that salt, e.g. salt, right? We know that salt doesn't just boil off, okay? If the solute is non-volatile, right, like salt, okay, then we know that none of it goes into the vapor. right? So that means that our total in the vapor has to be, so if we know that we have the mole fraction of, we know that the mole fraction of the solute in the vapor, since it's non-volatile, none of it went up, is going to be very, very close to 0. All right? That also means, right, so if we know that this is our fraction of solute, we know that the other part, so if the fraction of solute is added to the fraction of solvent, that will equal 1, right? Because we only have the solute and the solvent, and both of those fractions must add up to equal 1, okay? So that means that if the solute is 0, then the solvent has to equal 1. So Y of the solvent is equal to 1, right? And that's our mole fraction in the vapor. So that means that all of our fraction in the vapor comes from our solvent, right? And that should make sense because none of our solute went up into the gas, all right? If you have a 2-component mixture, you can always use that equation to get out the other component, all right? So say, for example, I'll do that later. We'll do it for a volatile component. All right, so we know that we have our mole fraction of the vapor of the solvent equal to 1. So that means that if we plug all of this in for our solvent, you'll want to do it for your solvent. We have X of the solvent. We have P of the solvent pure. Then we have Y of the solvent. And we have P total. Right? Y of the solvent in this case, right, for a non-volatile component, Y of the solvent is equal to 1. So that means that we have 1 times P total if we have a non-volatile component. Okay, because remember, we just showed that our Y of the solvent was equal to 1. Okay, so that means that this depends, our total pressure depends on the mole fraction of the solvent. All right, so doing an example on page 8 or on slide 18. What would be the P of, what would be the P total, right, or the P of the solution? For a solution that contains 3/4 non-volatile components and 1/4 solvent. Well, what is our mole fraction of our solvent? This is going to be 1/4, right? That would mean that the mole fraction of the solvent is equal to 0.25, right? That's 1/4. And then we would take that and we would multiply it by our pure component vapor pressure of the solvent. So our P total, right? Let's say that we had this solvent at, or rather with a P solvent equal to 1 atmosphere, then that would mean that our P total was equal to 0.25 times 1 atmosphere, right, because we have our mole fraction of our solvent, times our pure component vapor pressure, and that would be equal to 0.25 atmospheres. Notice that even though our pure component solvent was 1 atmosphere, since we have a non-volatile component and we have particles in our solution, it lowers our vapor pressure to 0.25 atmospheres. And we will continue to look at some of our other colligative properties next time.